All right, now I'd like to try some mental estimation problems. Here, I'm not going to try and get the exact answer. I'm just going to try and get close and try and do it pretty quickly. Give me a 3-digit number.
362.
362. And another 3-digit number.
457.
Multiply those together on the calculator. You should get about 165,000, 166,000, somewhere around there. Good. Let's try square roots. I don't know if your calculator does it, but I think yours does. Give me a 2-digit number, and I'll try and calculate its square root.
33.
33. Okay, so that should be about somewhere between 5.7, 5.8.
Yes.
Yeah? How about a 3-digit number this time?
124.
124. Okay, so that should be about 11.13, somewhere in that ballpark.
Exactly.
Great. In this lecture, we'll see how we can apply what we've learned to obtain good estimates. Using mental estimation techniques, you can come up with approximate answers to large problems that we couldn't do in our head because of memory limitations. We'll also be able to get especially rapid answers to everyday questions where you don't need to know your answer to the last penny or decimal point. Let's start with mental estimation of addition and subtraction problems. Here, we only need to consider problems where the numbers are about the same size, since otherwise the answer is approximately the larger number. For example, if my first number is 7 million and something, and my second number is 2,000 and something, then their sum and difference would still be about 7 million. So, how do we estimate the answer to addition and subtraction problems? In a word, rounding. Suppose you heard the problem 8,532 plus 3,259. Now, with 8 digits in the problem, it would be a challenge even to just repeat the problem. But if we round each number to the nearest 1,000, then we can estimate our answer as, all right, listen to the numbers again. 8,532, we'd round that to 9,000. Plus 3,259, we'd round that to 3,000. 9,000 plus 3,000 is 12,000. The exact answer is 11,791, so it's pretty close. If you rounded both numbers to the nearest 100, you'll usually get a better estimate. Here we'd have 8,500 plus 3,300, which is about 11,800, and that's even closer. The same idea applies to subtraction. Rounding to the nearest 1,000, our problem 8,532 minus 3,259 is about 9,000 minus 3,000, which is 6,000. Rounding to the nearest 100, we'd have 8,500 minus 3,300, which is what? About 5,200. And that's much closer to the exact answer, 5,273. By the way, it's worth repeating that this is another reason why we like to do our mental math from left to right instead of from right to left. Working from left to right forces us to pay attention to the most significant digits. I find the rounding method to be very helpful when estimating the grocery bill. As each item is rung up, I will round it to the nearest 50 cents. So for example, $3.33 would round up to $3.50. Or in my mind, I just might think 3.5. But $3.23 would round down to $3. Okay, what if we're right in the middle? What about $3.25? Should we go up or down? I will either go up or down depending on what gives me a whole number. So if I'm holding on to $18 as my running total and I have to add 3 1/4, I'll call the total 21. But if I'm holding on to $18.50, then I'll round that 3 1/4 up to 3.5, so that when I add those together, 18.5 plus 3.5, I'll have a nice even $22. Let's estimate the total of the following prices from a recent grocery bill. All right, actually they're the first few digits of pi, but we can imagine it's my grocery bill. Okay, so the first item was $3.14, so I'll think 3. The next item is $1.59. Well, let's see, $1.59, I think 1.5. Adding that to the 3 gives me 4.5. The next item is 26 cents. Well, I'll round that to 50 cents. 4.5 plus 50 cents gives me $5. The next item is $5.35, so I round that to 5.5. I have 5 plus 5.5 is 10.5. Finally, if the last item is 89 cents, I round that to $1 to get, let's see, 10.5 plus 1 is 11.5. The actual total is $11.23, so this estimate's pretty close. Using this method in practice, the overestimates and the underestimates tend to balance each other out, and your final estimate is usually within $1 of the exact cost. Let's move on to multiplication. Now, here what the most important thing to know about a multiplication problem is the order of magnitude of your answer. Is your answer in the thousands, or the tens of thousands, or the hundreds of thousands, or the millions? The general rule of thumb for multiplying two numbers is this. If the first number has x digits and the second number has y digits, then their product will have x plus y digits, or maybe x plus y minus 1 digits. Let me say that in English. The length of the product is the sum of the lengths, or maybe one less. So, for example, if we multiply a 5-digit number by a 7-digit number, then the answer must have how many digits? A 5-digit times a 7-digit is going to be a 12-digit number, or maybe one less, 11 digits. So it's a 12-digit or 11-digit number. So which one will it be? The longer or the shorter number? To answer this question, we multiply the first digit of each number. If that product is 10 or more, then it's definitely the longer number. If the product of the initial digits is less than 10, then the answer could go either way, but if it's the longer number, then the answer will begin with the digit 1. Here, let's look at some examples when we multiply two-digit numbers together. If we multiply two two-digit numbers together, how long is the answer going to be? It's either going to be 2 plus 2, 4 digits, or 1 less, 3 digits. Which one? Oh, first of all, why is that true? Let me say that for a moment. If I'm multiplying two two-digit numbers together, the smallest possible answer would be 10 times 10, which is 100, and that's a 3-digit number. The largest problem I could have would be 99 times 99. That's less than 100 times 100, which is 10,000. So your biggest answer has to be below 9999, which is a 4-digit number. Okay? All right, so now let's look at some actual problems. Let's say 42 times 67. Well, that's a 2-digit times a 2-digit, and so it's a 3-digit or a 4-digit number. But when we multiply the initial digits, 4 and 6, that's bigger than 10, so we definitely have a 4-digit number. All right, in our next two examples, the initial digits begin with are 2 and 3, right? And so 29 times 36 happens to be a 4-digit number, whereas 24 times 35 is a 3-digit number. When the product of the initial digits is less than 10, the answer could go either way. On the other hand, if the product of the initial digits is 4 or less, then it's definitely the smaller answer. Like in this problem, 17 times 49, the initial digits are 1 and 4, so the product has to be below 20 times 50, 1,000. So we're going to be left with the smaller answer, the 3-digit number. For a better estimate of the answer to 42 times 67, we'd round both numbers to the nearest multiple of 10. So 42 times 67, in your head you might say, well, that's about 40 times 70, which is 2,800. The exact answer is 2,814. Okay, you tell me, if we multiply a 3-digit number times a 5-digit number, then the answer will have how many digits? 8 or 7. It's either in the millions or the tens of millions. So if I had a problem like 1, 2, 3 times 4, 5, 6, 7, 8, then since the leading digits are 1 and 4, their product is 4, the answer is going to have 7 digits, not 8. So the answer is in the millions. Now, if you want to be more precise than that, for a good estimate, you might just look at the leading digits, 12 and 45. 12 times 45, let's see, that's 45 times 2 times 6, 90 times 6 is 540. So I know the answer begins with like a 5 and a 4, so I think my answer is a little more than 5.4 million. Sometimes you can estimate large problems without counting the individual digits. Instead, we make use of words that we already have. For example, something with 3 zeros is in the thousands. 6 zeros is a million. 9 zeros is a billion. 12 zeros is a trillion. So for a problem like 3,141 times 5,926, that's approximately 3,000 times 6,000, which is 18 million, because 1,000 times 1,000 is a million. But now let's turn our attention to division. Just like with multiplication problems, the most important point is to get the right order of magnitude. The rule for division is a lot like the rule for multiplication. The length of the answer is the difference of the lengths of the numbers being divided, or one more. This is sort of like the opposite of the multiplication rule. In the multiplication rule, that the length of the answer was the sum of the lengths, or possibly one less. When we do division, the length of the answer is the difference of the lengths, or possibly one more. So for example, an 8-digit number divided by a 3-digit number will have how many digits before the decimal point? Well, let's see. 8 minus 3 is 5. So the answer will either have 5 digits or 6 digits. So which one will it be? The longer or the shorter number? The answer for division problems is even easier than the answer for multiplication problems. Again, we look at the first digits, but instead of multiplying the first digits, we don't divide the first digits, we simply compare the first digits. More specifically, if we divide, let's say, the number A by the number B, if the first digit of A is smaller than the first digit of B, then we have the smaller choice. So for instance, if I took the 8-digit number 1, 2, 3, 4, 5, 6, 7, 8 divided by the 3-digit number 9, 8, 7, 8 minus 3 is 5. So do we have a 5-digit or a 6-digit number? Well, since 1 is smaller than 9, it's the smaller choice. It has 5 digits. On the other hand, if the first digit of A is larger than the first digit of B, then it's the larger choice. So in this next example, the 8-digit number divided by the 3-digit number, since 2 is bigger than 1, the number of digits is 8 minus 3 plus 1, which is 6 digits. If the first digit of A is the same as the first digit of B, then we have to compare the first and second digit of each number. All right, so for example, with a 6-digit number divided by a 3-digit number, let's do a few examples here. How many digits will be in our answer? Either 3 digits or 4 digits, right? So if it's 1, 2, 3, 4, 5, 6, divided by 789. Since the first number has a smaller leading digit, it's the smaller choice, the 3-digit number. Whereas in this next problem, where we have 2, 3, 4, 5, 6, 7 divided by 1, 2, 3, since the first digit of the 6-digit number is larger, then we have the larger choice, the 4-digit number. And in here, if I divided 1, 2, 3, 4, 5, 6 by 1, 6, 1, I now compare 12 with 16. Since 12 is smaller than 16, it's the smaller choice, the 3-digit number. So here's an example. Let's say your town needs $4 million by taxing each home. $4 million, that's a big number. It's 7 digits long. And let's say there are 12,000 homes in your town. 12,000 has 5 digits. Then how much will it cost each home? Now our answer will have 7 minus 5 or 7 minus 5 plus 1. Which will it be? How many digits? Well, 4 is bigger than 1, so it's the larger choice. It's 7 minus 5 plus 1, 3 digits in your answer. And since 4 divided by 12 is about 0.333, the answer will be about $333. Okay, let's try an astronomical calculation. How long does it take light from the sun to reach the Earth? Since the sun is 93 million miles away and light travels at about 186,000 miles per second, the number of seconds will be, well, it'll be the answer to the division problem, 93 million divided by 186,000. My first step would probably be to simplify those numbers by dividing both of them by 1,000. So now I'm thinking about 93,000 divided by 186. Now the answer is going to have how many digits? I've got a 5-digit number divided by a 3-digit number, which means my answer will have either 2 digits or 3 digits. And since 9 is bigger than 1, it's going to be a 3-digit number. Now, as it happens, we can get a very accurate estimate here. To do 93,000 divided by 186, notice that 186 times 1,000 is 186,000. And that's twice, exactly twice, 93,000. So that means that 186 times 500 will be 93,000. Therefore, 93,000 divided by 186 is 500 seconds, or about 8 minutes, 20 seconds for the light from the sun to reach the Earth. Here's another physical estimation problem. How long is this table? You may not have a tape measure handy, but your hand is always handy. Your body is like a walking yardstick, and it's worth knowing things like the width of your hand from pinky to thumb, or the size of your footsteps, or parts of your hand that measure to almost exactly 1 or 2 inches, or 1 or 2 centimeters. For example, in my case, my pinky to thumb length is almost exactly 20 centimeters. That's about 8 inches. And the length of my index finger from top to bottom is almost exactly 7 centimeters. Multiply that by 0.4, that's about 2.8 inches. Using these, I can estimate the length of this table. Okay, so let's do it. Each hand length is 20 centimeters, so I'll count by 20s. Right? 20, 40, 60, 80, 100, 120, 140, just a tad more than 140. So that's 140 centimeters. If I multiply that by 0.4, that's about 56, maybe 57 inches. If I look at the side of this table, I have 20, 40, 60, 80. Whoops, I overshot by almost the length of a finger. That's 7. 80 minus 7 is 73 centimeters. So that would be about 29 inches, 28, 29 inches. The next guesstimation application combines addition, subtraction, multiplication, and division. It begins with a problem that could well appear on a standardized test. Suppose you write a document and you send it to 2 proofreaders. One of the proofreaders finds 25 typographical errors, the other finds 36 typos, and there were 15 typos that were found by both of them. The question is, what were the total number of different typos found? Was it 30, 46, 61, 73, or the answer cannot be determined from the given information? You may want to pause to think about what your answer would be. The answer is B. There were 46 different typos found. Together, the reviewers found 25 plus 36, that's 61 typos, but 15 of those errors were counted twice. Thus, we subtract 15 from 61 to get 61 minus 15 is 46 typos. That was answer B. But now here's a harder problem. How many errors remain in the document? Although there's not enough information to answer this question with certainty, there's a pretty good estimate due to the great mathematician George Poya, author of the classic book, How to Solve It. If the first reader finds X typos and the second reader, acting independently, finds Y typos, and there were Z typos found by both of them, then by the logic of the last problem, the number of different typos reported is X plus Y minus Z. Poya showed that the best estimate for the total number of typos in the document, instead of being X plus Y minus Z, it's X times Y divided by Z. So in this problem, X is 25, Y is 36, that's how many typos each proofreader found, and Z was 15, the number of typos found by both of them. So the expected number of typos is 25 times 36 divided by 15. 15 has a factor of 5 and 3, and when I cancel a 5 from the 25 and I cancel a 3 from the 36, I'm left with 5 times 12, which is 60. So, how many typos do we expect left in the document? Well, we found 46 of them already, and Poya estimates that there are a total of 60 in the document, so we think there should be about 60 minus 46, about 14 typos left. What's cool about this answer is it does not depend on how long the article is. So if this document was like the first draft of a novel, 14 typos might be okay. But if the document was a 2-page memo, you may want to check it more carefully. Let's look at the estimation of sales tax or value-added tax. If the tax is a whole number, like 4%, then it's really just a straight multiplication problem. For instance, if the purchase of a car was $23,456, then to estimate 4% tax, I'd take 23,000 times 0.04. Let's see, 23,000 times 4 is 92,000. When I divide that by 100, that's $920. The exact answer is a little over $938. If the tax is not a whole number, let's say it's 4.5%, I'd calculate the tax using 4%, just like we did before, but then I would divide that tax by 8 to get the additional 0.5%. The reason that works is I'm taking that 4%, dividing it by 8, and 4 over 8 is a half. So in the previous example, the 4% tax estimate was $920. If I want 4.5%, I just take that 920 and divide it by 8. If you divide 920 by 8, you get 115, and if you add that to 920, you get an estimate of $1,035. This is similar to the tip that my mother taught me long ago for figuring out 15% tips at a restaurant. She would do 10%, then add half of that to get the additional 5% to get a 15% tip. So for example, if it was $42, the tip would be $4.20, that's 10%, plus half of that, $2.10, to get $6.30. With practice, you'll find these calculations of tips and taxes are not all that taxing. Speaking of money, let's do some calculations that are more interesting, beginning with the famous Rule of 70. Suppose that a bank offers you an interest rate of 3% per year. If you keep your money in the bank, how many years will it take for your money to double? The Rule of 70 says that the answer is going to be 70 divided by the interest rate. So with an interest rate of 3%, we divide 70 by 3 to get 23 and a third, so it'll take about 23 years for your money to double. With an interest rate of 5%, you do 70 divided by 5, which is 14. So it should take about 14 years for your money to double. Indeed, if you took $1,000, then after 14 years, you'd have 1,000 times 1.05 times 1.05 times 1.05, 14 times to get a little over $1,979. By the way, the reason why this rule works is based on natural logarithm and the beautiful number e studied in pre-calculus. But fortunately, we do not need to use any higher mathematics to apply this rule. Here's another interesting calculation, and although the exact formula requires a calculator, we can still do some useful estimating. Besides, it's such an important formula, and it's so rarely taught in school that I feel obligated to include it. Suppose you borrow $200,000 to buy a house, and the bank charges an interest rate of 6% per year, compounded monthly. What that means is that it's charging you 6 over 12, 0.5% interest for every month of your loan. Suppose the bank gave you 30 years to repay your loan. How much will you need to pay each month? All right, now before I give you the exact answer, let's do some ballpark estimates. First of all, the number of monthly payments is how many? You've got 30 years to pay it, 12 months in a year. That's 30 times 12, 360 monthly payments. Now, if the bank did not charge you any interest, that's a big if, but if the bank did not charge you any interest, then your monthly payment would be $200,000, the size of your loan, divided by 360. You can simplify this by dividing everything by 10 to get the problem 20,000 divided by 36. Even mentally, you could divide everything by 4 to get 5,000 divided by 9, or equivalently 1,000 times 5/9. And since we know the fraction 5/9 is about 0.555, then this would give you a monthly payment of about 1,000 times 0.555. In other words, about $555 per month. That's if the bank did not charge you any interest. But remember, the bank is charging you 0.5% of interest every month. So your monthly payment will be higher than that. How much higher? A lot higher. Okay, what is 0.5% of $200,000? That's the amount of interest you're going to owe in the first month. Well, 1% of $200,000 is $2,000. So 0.5% would be $1,000. So a quick estimate of your monthly payment would be $1,000 just to cover the interest for that month, plus $555 to go towards the principal. Add 1,000 plus 555, you get $1,555. Now, this is an estimate of your monthly payment, but it'll always be on the high side, since after one payment, you wouldn't owe the bank $200,000 anymore. You'd owe it $555 less than that. So, summing up, we know that our monthly payment must be somewhere between $555 and $1,555. It would be tempting to estimate your monthly payment as the average of these two numbers. $555 and $1,555 have an average of $1,055, which is a better guess than either of these numbers. But here's a more accurate formula for your monthly interest, but it definitely requires a calculator. If the amount of money that you borrow is P, as in principal, and you're charged a monthly rate of I, and you have M months to pay it back, then your payment will be given by this formula. P times I times 1 plus I to the M divided by 1 plus I to the M minus 1. Let's look at some numbers. In our last example, P was $200,000. The interest rate per month was 0.5% or 0.005. And the monthly payments, M, was 360. I'm sorry, that's the number of months, is 360. So plugging that all in, the monthly payment would be given by this. Now, if you use a calculator or even a search engine to compute 1.005 to the 360, that gives you 6.022. Then the entire formula here simplifies to $1,199.10. So our monthly payment is about $1,200 a month. This seems reasonable since it's in between our lower bounds and upper bounds of 555 and 1555, and it's higher than the average of those numbers. I've included additional examples of these problems in the course guidebook. Finally, I'd like to turn our attention to the estimation of square roots. The square root of a number, when multiplied by itself, gives you the original number. So, for example, the square root of 25 is 5, since 5 times itself is 25. And the square root of 100 is 10, since 10 times itself is 100. Numbers like 25 and 100 are called perfect squares, since their square roots are whole numbers. On the other hand, a number like the square root of 2 evaluates to something like 1.414, which is not a whole number. Square roots arise in many physical and statistical calculations. For example, in a right triangle, the length of the hypotenuse is the square root of a squared plus b squared. For example, if we can estimate the length and depth of this table, then we can use square roots to estimate the length of the hypotenuse, the length of the diagonal that goes from this corner of the table to that corner of the table. In statistics, if n randomly chosen people are asked a yes-no question, then the margin of error on the survey is 1 over the square root of n. What this means is that 95% of the time, the sample's average will be within 1 over the square root of n of the true average. For example, if 100 people are chosen at random and asked if they approve of the president's policy, then since the square root of 100 is 10, 95% of the time, the results of the sample will be within 1/10 or 10% of the national approval rating. Whereas if 900 people are surveyed, then since the square root of 900 is 30, the margin of error is 1 over 30, or 3.3%. So here, 95% of the time, the survey sample is within 3.3% of the national approval rating, even if the nation has millions of people. So how do you find square roots when you don't have a perfect square? Like, how would you find the square root of 40? I like to estimate square roots using the divide and average method. Here's how it works. To find the square root of a number like 40, you start by taking any reasonable guess. Now here, 6 squared is 36, and 7 squared is 49. 40 lives between 36 and 49, so the square root has to lie between 6 and 7. And now since 6 squared is closer to 40 than 7 squared is, I'll make an initial guess of 6. All right, now, first step, we divide by 6. 40 divided by 6 is 6 with a remainder of 4. That's 6 2/3. In other words, 6 times 6 2/3 is 40. Now, since that means that 6 times 6 is going to be less than 40, that tells me that the square root of 40 is bigger than 6. And 6 2/3 times 6 2/3 will be bigger than 40, so that tells me that the square root of 40 is less than 6 2/3. So the square root has to lie between 6 and 6 2/3. So next, we average those numbers, 6 and 6 2/3. Their average is 6 1/3, that's 6.33, so we'll estimate the square root of 40 to be about 6.33. The exact answer begins 6.32, so that's very close. In this lecture, we've been exposed to a lot of practical methods for estimating addition, subtraction, multiplication, division, square roots, and other physical problems. In the next lecture, I'll show you how you can do these problems and more almost instantly when you allow yourself pencil and paper, but using methods that they seldom teach you in schools. I estimate that you'll enjoy that lecture quite a bit.